So in this question, it says find the interval on which the function given here is concave. Now we know for something to be concave, okay, let's first of all draw the concave part. It's this, and let's not memorize. Let's just kind of understand. If it's concave, we know that the gradient is going to be doing what? Decreasing. So we then know that if the gradient is decreasing, then the rate of change of the gradient, i.e. d2y by dx squared, is going to be negative. So use your understanding to remember the result rather than trying to memorize it and getting them mixed up. So that's what we're trying to show. For it to be concave, that's what we want to aim for. So let's go and find the second derivative. We're given the function x, f dashed x, this first derivative, 3x squared plus 4. F double dashed x is equal to 6x. There's our second derivative. But we want to find out when it is concave. So for it to be concave, we want this second derivative to be, we want it to be less than 0. So we would say f double dashed of x must be less than 0 for curve to be concave. And we found out what f double dashed of x is. We can then 6x has to be less than 0. Therefore, x is less than 0. Yeah. So for x is less than 0, the curve will be concave. Find the interval. Okay. Let's take a look at another question then. Show that f of x equals to e to the 2x plus x squared is convex for all real values of x. So first of all, I'm going to look at that word convex, and I'm going to draw a few tangents to remind of what derivative. We can see that the gradients are increasing as we increase values of x. Therefore, we expect the rate of change of the gradient to be positive. Positive meaning greater than 0 for convex. It's a show that question, so we need to show that our second derivative is going to be greater than 0, is what we're going to aim to do. For all real values of x, we need to show that's the case. So let's go and work out my first derivative. Differentiating each term here, e to the 2x becomes 2e to the 2x plus 2x. Second derivative, differentiating this becomes 4e to the 2x plus 2. And we need to show that this is, we need to show that 4e to the 2x plus 2 is greater than 0. That's our aim. So how do we show that this to be greater than 0? A couple of ways we might approach this. We could visualize what this looks like. Graph it. 4e to the 2x plus 2 is essentially transformations applied to the function e of x. Yeah. So what does the e of x function look like? Going through that value 1, and there is an asymptote y equals to 0. This is the x-axis, that's the y-axis. That's e to the x, but what does all of this do? What does all of that do? First of all, let's apply the transformation in the x direction. There's only one transformation. It's times by a scale factor of 1/2. So if it times everything by a scale factor of 1/2, does the shape of that change? Yes, it does. The x values all get multiplied by 1/2, Will that 0 over 1 get affected? No, that stays where it is. Will the y equals 0 get affected? No. So what will happen is it will just look something like that. It will just become, we'll still have the same asymptote. So this will then be e to the 2x. Okay, let's go and then draw the transformations applied to that. What other transformations do we have? Now we've got y transformations. There's a scale factor of 4 in the y direction, and there's a +2 translation in the direction of 2. Which one do we apply first? In y direction, it's enlargement followed by translation. So let's go and apply the transformation here. Enlargement by scale factor 4 applied first will result in 0, 1 becoming 0, 4. Y equals to 0 remains as it is, 0 times 4, still what it is. And so our graph looks something like that. Okay, going through 0, 4 there, let me make that a bit clearer. Then what are we doing? We are translating it up by 2. So let's apply the next transformation and what that does. So if we apply the next transformation, what will it do? Y equals 0 now becomes y equals 0. Asymptote now becomes y is equal to 2. 0, 4 now becomes 0, 6. Everything has been translated up by 2. So what was this? This was, remember, 4e to the 2x, and this is now 4e to the 2x plus 2. As we can see, this function is what? The output 4e to the 2x plus 2 is always greater than 2. Yeah, so we can see from the graph that 4e to the 2x plus 2 is greater than 0 for all values of x. So this goes back to kind of our questions with domain and range that we covered in function. We are essentially trying to show what this output is going to be for this second derivative. The output's always going to be greater than 0. And when we are trying to show what the output's going to be going back to range, I said always try and visualize, look at what the graph looks like. Okay. Other ways you could do this, algebraically, for instance, well, we can say that e to the 2x is always going to be positive for all values of x, doesn't it? Isn't that true? Yeah, you can look at negative, very large negative value and a very large positive value. E to the 2x is always greater than 0. And we can see that. Can you look at that? E to the 2x is always greater than 0. So if e to the 2x is greater than 0, if we times something which is greater than 0, i.e. a positive number. So if we times this positive number, okay, so this is greater than 0, times a positive number by 4, it's going to be still positive. Plus 2 to that positive number, it's still going to be positive. Therefore, it's greater than 0. So that could be another logical answer, logical argument that you might write down. You would say e to the 2x is always greater than 0. Timesing it by 4 still keeps it a positive, greater than 0. Adding 2 still keeps it a positive. So we've looked at a graphical as well as a kind of a using the terms there, an algebraic kind of explanation to show that. And then lastly, this one here, which is asking you to find the coordinates of the point of inflection. Now, when we have a point of inflection, we know that the rate of change of the gradient is 0 at that point. So the rate of change of the gradient, referring to the second derivative, d2y by dx squared, is equal to 0 at that point. So go and find out what that is. dy by dx is equal to 3x squared minus 4x minus 4. d2y by dx squared is equal to 6x minus 4. And at the point of inflection, The second derivative is 0. Therefore, x is equal to 4 over 6, 2 over 3. It asks for the coordinates, so we need to go and find out what the y value is. Y is equal to 2 over 3 cubed minus 2, 2 over 3 squared minus 4, 2 over 3 plus 5. Tidy that up a bit. 2 cubed, 8 over 27 minus 4 times 2 is 8 over 9 minus 8 over 3 plus 5. Calculator, does that become? 47 over 27. So that's the coordinate of the point of inflection. How can we prove that this is the case? What would we do? How they might say, show that this is a point of inflection. I know they haven't said that here, but we've discussed it earlier. How do we show it's a point of inflection? Put the x coordinate into a gradient function. We need to look at a value. So remember what happens. Point of goes from concave to convex. So suppose this value here is x equals 2 over 3. We want to show that a value just before it is concave, and we want to show a value just after it is convex. So a point just before it, a point just slightly less than 2 over 3, well, we can use x is equal to 0.65. Yeah, because that's obviously 0.6 recurring there. So let's use 0.6 and 0.7. X equals 0.6, and a point after x is equal to 0.7. You would substitute that into our second derivative to see if it's concave and convex. So our second derivative d2y by dx squared at x equals 0.6 is equal to 6 lots of 0.6 minus 4. So 3.6 minus 4 minus 0.4. And then d2y by dx squared at x is equal to 0.7, which is just slightly greater than 2/3, is equal to 6 lots of 0.7 minus 4, 0.2. So it goes from negative, meaning it is concave, to positive, meaning it is now convex because the gradient is increasing. The curve goes from concave to convex when we substitute x values on either side. Therefore, x equals 2 over 3 is a point of inflection. So that would be the reasoning to show that there is a point of inflection, if that was the question. Okay, so you need to write a final statement. As there is a sign change for d2y by dx squared on either side of x equals 2/3, there must be point of inflection at x equals 2 over 3, where d2y by dx squared is equal to 0.